Okay, so in section 1.2, what we talked last time, looking at a bunch of graphs, we learned that the limit of f of x as x approaches c does not necessarily depend on the value of f at x equals c. What does that mean? So, for example, on the homework that you guys did last class, it was like you had a function as, oops, that's not what I wanted. I wanted the limit as x approaches 1 from the left of a function equaled something. You had like the limit as x approaches 1 from the right equaled something. Then you were asked also if the limit as x approaches 1 of that function, and you were asked what the function of 1 was, for example. Okay, sometimes these two things right here were the same, right? The function of x approaching 1 and the function at 1 were the exact same thing. In the case when they were not the same, there was something like it was, discontinuous. It was not at the same point from the left and from the right. Or maybe there was a hole at that point, right? So keep that in mind. But that's basically what we're going to do. We're going to look at specific examples of when these kind of things are the same, so we're able to plug in values into a function and evaluate them without having to graph it, okay? So it may happen, however, that the limit is precisely f of c, which is what I kind of showed with that f of 1 example, and in such cases, the limit can be evaluated by direct substitution. Okay, so we're just going to plug and chug a few things. So if I look at example A here, it says the limit as x approaches 1 of this function x squared minus 3x plus 5 over x plus 1. We are going to just plug in 1 anytime we see x. Okay, so I'm going to rewrite this as 1 squared minus 3 times 1 plus 5 divided by 1 plus 1. I know some of us can do this like mental math in our head. That's fine. I would like to at least see this step written down, and then you can give me the answer. But if I evaluate this, 1 squared would be 1 minus 3 plus 5 over 2, following order of operations from left to right. I would end up with 3 divided by 2. So the limit as x approaches 1 of this function is 3/2, or 1.5. Okay? Go ahead and do letter B for me. Same idea. You're plugging in that value of x into your function that is given to you, but make sure if you can simplify the radical, simplify the radical. Okay? I am seeing a lot of square root of 12. Did we all get the square root of 12? Okay, good. Then, if you can simplify that radical, please do. It's always best to simplify in math if you can. Yep, square root of 4 and square root of 3 is what that multiplies into. So 2 square root of 3 would be your final answer for this one. So the limit as x approaches negative 3 of this function equals 2 square root of 3. Okay, so that works when we don't get 0 in the denominator, right? When we don't have fractions. I can plug in values like this. However, the following ones, when we plug something in, when we use direct substitution, it's going to sometimes produce 0 over 0, which is the indeterminate form, okay, and we can't have that. So some methods that you're going to use in terms of getting rid of the 0 over 0 form is factoring or rationalizing the denominator. Okay, so these first two examples we're going to do using factoring. The next one we'll use rationalizing, and then you're also just going to have to kind of play around with things, like what algebraic things do you know that you can manipulate an equation by, okay? So if I look at letter C here, the first thing that you would do is, if I just said to evaluate this limit, is to test to see if you plug in 1, are you going to get the value output, right? So if I plug in 1 here, 1 cubed minus 1 over 1 minus 1, that is going to give me 0 over 0. Okay, so I can't do that. I have to do something else in order to solve this limit or evaluate this limit. So, anyone remember the difference of cubes formula? I'm going to write it out up here. So if I have a cubed minus b cubed, that would be the same thing as a minus b times a squared plus ab plus plus b squared there, okay? So we're gonna factor the top of this numerator here, x cubed minus 1. If I factor that, I would have the limit as x approaches 1 of x minus 1 times x squared plus x plus 1. And that's all divided by x minus 1. Yeah.
I thought for the...
All right, so with my x minus 1s, what's going to happen on the top and bottom? They simplify to 1. Yes, they don't cancel. They simplify to 1. Try and make you better mathematicians. Okay, so it's hard for me to even remember it. It's okay. So these simplify to give you 1, right? Which really could be like a hole at that point, right? Or it's going to be discontinuous at that point. Something is going to happen at that point, which makes it that 0 over 0 form. But now if I plug in 1 and I evaluate this limit as it approaches 1, using just the x squared plus x plus 1 part, we should get a number output, okay? So let's go ahead and rewrite this. I'm going to rewrite it as the limit as x approaches 1 of this function. And then I'm going to show that I'm plugging in 1, which means you don't need to write the limit anymore. So I'm plugging in 1. And if I evaluate that, we get 3. Okay, good math notation is like, don't drop the limit part until you actually find the limit, okay? So if you're doing some algebra and things and maybe you aren't putting the limit, that's fine. But at the very end, before you actually evaluate it, make sure you rewrite this kind of statement right here before you give me the value, okay? Does that make sense? Okay. All right, let's look at letter D. Letter D is a little bit easier in the terms of factoring. So go ahead real quick right now, factor the numerator, see what is going to simplify to 1, and then evaluate your limit as it approaches 2. Okay, if you need help, let me know. All right, so now I can go ahead and simplify both of those to be 1. And now I'm just evaluating the limit as x approaches 2 of x minus 1. And that would be 2 minus 1, which is 1. Questions on that one? Okay, let's look at the next technique then we're going to use. The next technique is going to be rationalizing the denominator and allowing us to evaluate it at 0 without getting an indeterminate form. Because if I plug in 0 here, if I plug in 0, I get 0 over the square root of 0 plus 1 minus 1, which if I evaluate that, I get 0 over 0. So that means we cannot just plug it in. We can't just use direct substitution. We have to do some sort of mathy thing, okay? That mathy thing is up to you to figure out. The mathy thing we're doing right now is rationalizing. So in order to rationalize this denominator, what am I going to multiply by?
Square root of x plus 1 plus 1.
Yeah, square root of x plus 1 on the top and on the bottom. So let's go ahead and do that right now. So I'm going to have the limit as x approaches 0 of x over the square root of x plus 1 minus 1 times the square root of x plus 1 plus 1 over the square root of x plus 1 plus 1. Okay, now when I multiply this, I still have not evaluated my limit. So I'm going to have x times the square root of x plus 1 plus 1. Oh, no, yeah, I didn't forget anything. We're good. And then divided by, remember when you're rationalizing a denominator, you're getting rid of that square root, right? So when I multiply square root of x plus 1 and square root of x plus 1 together, what am I left with? Just x plus 1, right? So I've got x plus 1. And then if I multiply this square root of x plus 1 with the positive 1, and I multiply the negative 1 with the square root of x plus 1, what happens with those terms? They simplify to 0, but yes, they cancel out, okay? And then we're only left with one last number down here, which is negative 1 times 1, right? So I've got another minus, not plus, I got another minus 1 there. Do we all follow with that distributing there? Okay. Good stuff. And now I'm just going to go ahead and simplify some things. I've got now the limit as x approaches 0 of x over square root of x plus 1 plus 1. Now, why do you think I didn't distribute?
Because the x's cancel.
Because the x's are going to simplify to 1. Okay? Yes. Those are going to simplify to give you 1. Because I forgot to say 1 minus 1, obviously that's going to go away. So now we're just left with the limit as x approaches 0 of the square root of x plus 1 plus 1. And now can I plug in that value and get an output? Yes. When I plug that in, I get the square root of 0 plus 1, which equals 2. Next example, last example on this page. Some other algebraic techniques we can use. If we've got fractions and fractions, and I've got 2 fractions in the numerator that have different denominators, could we make them have the same denominator? Yeah, right? Let's go ahead and do that and see what happens. So I'm going to multiply the first fraction there by 3. And I'm going to multiply the second fraction by 3 plus x. Okay, when I do that, I get the limit as x approaches 0 of 3 minus 3 plus x divided by 3 times 3 plus x, all divided by x. Another thing you can think when you see fractions and multiple division bars is think maybe we could rewrite it as in terms of a multiplication problem, right? So let's go ahead and simplify this. Distribute that negative. If you forget to put the parentheses around that, you might end up getting something wrong here with a sign. So make sure you're careful with that. I'm going to have the limit as x approaches 0 of 3 minus x divided by, we can distribute that on the bottom there. I get 9 plus 3x. And that's all divided by x. So 3 minus 3 simplifies and gives us 0. And now we are left with a negative x divided by 9 plus 3x, all divided by x. Now I realize some of you might do this like in less steps. That's fine. As long as you show some sort of work, I would be happy. Okay? All right, let's rewrite this as a multiplication problem then. Because if I rewrite it, what's going to happen? What happens with the x's?
They divide out.
Yeah, they divide out, simplify to give you 1, right? Dividing by x is the same as multiplying by the reciprocal of 1 over x. So those x's are going to simplify to give you 1. And now we are left with a limit, which when we plug in 0, we are allowed to evaluate it. All right, so let's go ahead and plug in our value of 0. So I'm plugging in 0 here. So this is going to equal negative 1 over 9 plus 3 times 0, which is just negative 1/9 for your answer. So as you're approaching 0 of this function, you will approach negative 1/9 for that intended height. Okay, so we're going to talk through these, and then we're going to do some examples. I'm going to maybe draw some pictures and rewrite some of these formulas a little differently. That maybe make a little bit more sense to you, so that you have some other things to look off of. So for theorem 1.1, okay, these are things that you guys already actually know, okay? If, for example, number 1, it says, as I approach some value, so let's say as I approach, let's rewrite this. Let's say I had the limit as x approaches 1 of 5. Okay, well, if I just say 5, in terms of a function, what is that going to look like?
5. Straight line.
Yeah, it's going to look like a straight line at 5, right? So imagine if you had a graph. Your graph would look something like this for that function, right? So no matter what value I approach on my x's, right, I'm always going to have that same output of whatever that number was. For this one, it's 5. Okay. Now for number 2 is a little different. If my function is x, this is also a straight line, but it has a slope of what? Has a slope of 1, right? So if I were to draw this picture of this function, it would look something like this. Okay, meaning that as I approach any number, okay, so like if I approached 1, my limit as I approached 1 of x would also be 1, right? Because the x value is going to give you that exact same y output. Okay, if I was at 2, I would be approaching 2. If I was at -1, I would be approaching -1. Okay? And then the last one there is if I have any type of function to a power. If I have x squared, or if I have x to the 3rd power, okay? It's always going to be approaching, or sorry, your limit as it approaches that function at any number is always going to be that number to that power, the same power, okay? So it could be any degree, x to the 5th. If it was approaching 2, it would be 2 to the 5th. Okay, maybe let's write that out as an example. So if I had the limit as x approaches 2 of x to the 5th, that would give me 2 to the 5th. Which makes sense, right? Because think about plugging in the value. If you're evaluating this limit as x approaches 2 of this function, what we were just talking about analytically is plugging in those values, right? So if I plug in 2 to that function, 2 to the 5th power gives you your answer, okay? All right. Next one are properties of limits. And these ones are all pretty straightforward. We're going to rewrite a few of them to maybe make a little bit more sense. So we have these 2 limits. We have the limit as x approaches c of function f of x that equals L, some number, and okay, and then I've got the limit of g of x approaches, or sorry, as x approaches c, you will get k. Okay, so again, those are just numbers. L and k are positive, or sorry, not positive, but they are numbers that you will get as an output. So if I was looking at this example right here and I was given something like the limit as x approaches c of some factor multiplied by a function, okay? Your answer is really just think about taking that b out, and it would be like b times the limit as x approaches c of f of x. So you find out what that limit is, and then you just multiply it by whatever scalar you are given. Okay, for the next 3, it's basically doing whatever operation is given to you, and you are just doing that operation also with the limits. You're finding the limits individually, and then you are either adding them together, multiplying them together, or dividing them, okay? So let's rewrite this because I think the notation is a little funky. It does make sense to me, but it might not quite make sense to you. So if I rewrote this as the limit as x approaches c of f of x plus the limit as x approaches c of g of x, that would give me my same answer of L plus or minus k. Sorry, I should put a plus or minus symbol there. Okay, feel free if you want to rewrite that same thing for the next 2. It's the same idea. Instead of adding, though, we would be multiplying for the next one. You multiply both of those limits individually, okay? And then if we're dividing, you find the limits individually, and then you divide them. Does that notation make sense? Okay. And then your last one is to the power. Okay, so if I'm given a limit as x approaches c of some function and it's raised to a power, don't worry about it until after you find the limit. Find the limit first, and then just raise it to that same power. So a few problems like this that you'll see on our examples here in a minute are going to be maybe the kind of problems that I would ask you on your quiz on Friday, okay? They wouldn't be super, super complex ones in terms of these properties, like using the special trig limits. I would not expect you to know that by Friday, okay? All right. And then this next one is the limit of a composite function. Okay, you've seen composite functions before. They look like this, right? F of g of x, but now there's a limit term in front of it, Okay, so the way that we evaluate it is listed here. We're going to do example, and I think it'll make a little bit more sense on the second page here. Okay, but you're finding the limit of the inside function. Okay, and then you are finding what that function is of f, or whatever that function on the outside is, at whatever the limit value that you got evaluated was. Okay? All right. And then we've got the squeeze theorem. I'm going to draw a picture of this one because I think that makes the most sense. So if I have a coordinate plane, the notation here says I've got three functions, h of x, f of x, and g of x. Those notations, those greater than or equal to symbols or less than or equal to symbols, right? They mean that f of x is in between those two functions, okay? For all of the x values on our open interval containing c, except possibly at c itself. So if I had a function and it looked like this, we'll call that h of x. And if I had a function called g of x and it looked something like that. What it is saying is, like, for example, if I am approaching 0 for both of these functions, and if I wanted to find the limit as x approached 0 for both of these, what would you guys say the answer is? 0, right? It's technically crossing here. It might not look like it, but it is crossing there, okay? If I was also given, or I was told that there's another function that was in between these two that looked something like this, or I was told that it was in between g of x and h of x, I know that since those other limits are approaching 0 at 0, for f of x, as x approaches 0, I would also get an output of 0, okay? So that's what this notation here and here is saying. Let's do an example, though, and it will make more sense. But the basic idea is you're given two functions outside of each other, and then the function inside, as you're approaching some value, it's going to squeeze it to the same value, okay? So an example of something like this for the squeeze theorem could be this. You'll want to write this down. So if we were given something, I'm going to choose a smaller font there. So if we had 3x is less than or equal to your function f of x, and it's less than or equal to x cubed plus 2, evaluate the limit as x approaches 1 of f of x. Okay, so we know that the function f of x is in between these two functions on the outside, which are technically the h of x and g of x functions, right? In terms of that notation that we have up there from theorem 1.8. What you might see on your answer key for your homework, if you look at it, I'm going to write it the same way so that way you're aware of what the notation is saying. It's like if I look at the limit as x approaches 1, right, because that's what we're trying to find, from the left. What I mean by that is I mean the left bound, right? So that 3x function. Okay, I'm going to find what the limit is as I plug in 1 of 3x. So if I evaluate this, if I plug in 1, I get 3 times 1, which is 3, right? So the limit as x approaches 1 of 3x equals 3. Now I'm going to do the exact same thing, but for the right-hand limit. If the right-hand limit is also 3, then I know that the limit as x approaches 1 of our f of x function has to also be 3 based on the squeeze theorem. So the limit as x approaches 1 from the right of the other function, that would equal 1 cubed plus 2, which is also 3. Okay, so to answer this question, since I know both of these things are equal to 3, right, we can say, anyone ever see these 3 dots before in terms of math? This is like therefore or since. You might see it in the future in some classes. It's just kind of a way to justify. So like you found 2 things. Now, since this, therefore, we can say that the limit as x approaches 1 of f of x is going to equal 3 because, or by, the squeeze theorem. Then the last thing there is just the two special trig limits is if you approach 0 of sine of x over x or 1 minus cosine of x over x, you will get the following outputs of 1 and 0. Okay? Again, that won't be on your quiz, but you will need to know it. You will want to have it memorized. All right, let's look at example 1 here. Quick and easy. Plugging in these values, you're given two functions. If I evaluate the limit at -3 for f of x, that means I'm just plugging in -3. So -3 plus 7 is 4. Okay, next one says, what's the limit as x approaches 4 of g of x? Well, I plug in 4 for g of x, and I get 4 squared, which equals 16. Okay, this is one of those composition ones that is a little kind of confusing. So let's go ahead and rewrite it like this. So I've got the limit as x approaches -3 of the limit as x approaches -3 of our function f of x. Okay, we have to evaluate the limit as it approaches f of x first. Okay. If I evaluate that limit as x approaches -3 at f of x, that was letter A, right? So it would be 4. So as the limit as x approaches -3 at 4. Okay, oh, I forgot a g in front of this here. There's a g. Okay, now the limit as x approaches -3 of g of 4, I plugged in 4 into my function already for letter B, and we got 16, right? So this would be the same thing as the limit as x approaches -3 of 16. Well, if I have the limit as x approaches any number of a number, it's just going to be that number. So the limit as x approaches -3 of 16 is equal to 16. So you find the limit of the inside, okay, and then plug that in to your outside function, whatever that function is. Okay? All right. Number two, we have two functions here. I've got the limit as f of x, or as x approaches c of f of x. That's 3/2. And then I also have the limit as x approaches c of g of x, which is 1/2. Okay, so these are using those like properties theorem 1.2 on the previous page. These are kind of the problems that you might see on your quiz on Friday. Some simple property problems and maybe a few analytical problems that you would solve. So I already know what the limits are. I just have to do whatever operation is telling me. Okay, so this 4, we could rewrite this, since it's a scalar multiplication, as 4 times the limit as x approaches c of f of x, which is actually just 4 times 3/2, right? Which is 12 over 2, which is 6. Yeah. Okay, letter B. I'm taking the limit of both things and I'm adding them together. So I've got the limit as x approaches c of f of x is 3/2, and I'm adding 1/2, and it's nice because they've got the same denominator. So I've got 4/2 or 2 for your answer. C and D are the exact same as B, except for you're doing a different operation. So go ahead and do letter C and D right now for me, and check with your neighbor, see if you get the same thing as them. All right, did you guys get 3/4 and 3 for both of those? Good stuff. Okay. Now, kicking it up a notch here, we are going to need to know those trig limit properties on the back page. Okay, so theorem 1.9. I'll write them over here as well. If you want to, you can do as well. So the limit as x approaches 0 of sine of x over x equals 1. That is one of them. And also, just kind of for you to think about, if it was written the other way, if it was x over sine of x, it would still be equal to 1. Okay? Oops. And then we've also got the limit as x approaches 0 of 1 minus cosine x divided by x, that one equals 0. So those are your trig properties from the previous page. So first thing you can do is if you are evaluating this limit, we can just plug in 0 and see what we get. I'm going to kind of fast forward that step because if I plug in 0, I'm going to end up with 0 over 0, which does not work because it's indeterminate, so I need to do something else. Okay? So I know that the sine of x over x equals what? 1. I know that. Okay? So we could rewrite this as the limit as x approaches 0 of 3 over 2 times the limit as x approaches 0 of sine of x over x. Same thing, right? I just rewrote it. We know this is going to be 1. And then if I approach 0 at 3 over 2, what am I going to get? 3 over 2. So your limit for this one is just 3 over 2. Okay, number 4 is the one that's got 2 different ways we can do it. I'm going to show you both ways just to kind of help maybe remember some things from pre-calc algebra. But same idea. If you plugged in 0 for this and checked, you would get 0 over 0. Okay, in determinate form, we can't have it, so we're going to have to do something else in order to evaluate this limit analytically. So, anyone have any ideas of what we could do if you're given this problem? Split. I heard a few things. What did you say?
Split into like 1 minus cosine and then like times cosine.
Are you saying difference of squares?
Yeah.
Yes, difference of squares. We could factor. Factoring is one option. What is another option? I heard someone back here say it. Yeah.
Doesn't like 1 minus the cosine squared equal sine?
Yeah, it does. Equals sine squared x. So we're trig identities and we're going to show factoring. Okay? Let's go ahead and do the trig substitution first. So that's the first option that we're going to try. So trig substitution. We know that 1 minus cosine squared of x is equal to sine squared of x. So I can rewrite this as the limit as x approaches 0 of sine squared of x divided by x. Which, if we see a sine x over x, we should be thinking, oh, okay, that's one of those special ones, which equals 1. However, we've still got some stuff left over here, right? So if I rewrite this as the limit as x approaches 0 of sine of x times sine of x divided by x, right? I can find the limit of each of those things and multiply them together, correct? I know the limit of this is 1. Now I just need to evaluate the limit as x approaches 0 of sine of x. If I plug 0 in here, sine of 0 is equal to, sine of 0 would be 0. Think about on your unit circle, you're going over. Can't forget that unit circle stuff. Any questions on the trig substitution part? Okay, so we should get the same answer doing factoring. We should still get 0. So let's try the factoring method. Okay, anytime you've got difference of squares, you can use that formula of a plus b times a minus b. Okay, so if I evaluate this limit, I would rewrite this as 1 plus cosine, oops, not squared, just cosine of x, times 1 minus cosine of x. And that's all being divided by x. Okay, if we see a 1 minus cosine of x, that is also a trig rule there that we have to remember. It's equal to 0. Okay? So this piece right here evaluates to give me 0, right? Do I really need to do anything else? No, because anything times 0 is going to give me 0, right? So even if I evaluated this limit at 0 of 1 plus cosine of x, whatever that is equal to, I would end up getting 0. So you can just go ahead and stop there, say equals 0, and you are done. Okay, so again, a few different options you can look for. Remember, everything that we've done up till now will be used in calculus. Okay? So if you ever get across something that you're like, I have no idea what this is, or when we learn this, you might just have a gap somewhere in your learning, and just come talk to me and we can work through it. Okay?